Okay, so here's how we formally define vertical asymptotes. The line x equals a is a vertical asymptote, right, of the graph of a function. Okay. X equals a is a vertical asymptote of y equals f of x if, right, either of these happens if the limit of f of x as x approaches a from the positive side is infinity, or as x approaches a from the negative side is infinity. Now, that's what the wording says. Does it make sense? Well, let's see. If I have the x-axis, the y-axis, and some function is to be graphed here. Now, suppose this is x equals a. If, as x approaches a from the positive side, right, the limit of it is positive infinity, that means it goes up, then it has an asymptote there, a vertical asymptote. Does that make sense to you? Yeah. Of course it does. And how about if, as x approaches a from the negative side, it goes to infinity? Does that make sense to you? Of course it does. So that's how formally a vertical asymptote is defined, right? And when does that happen? That happens when the denominator of the simplified f of x is 0, right? That's when we get a vertical asymptote. Okay, so let's find the vertical asymptotes of these graphs and then describe the behavior to the left and the right of each vertical asymptote. Okay? All right, so here, when I factor these, I get x minus 1, x plus 1 over 2, x plus 2. So a vertical asymptote would be at x equals negative 2, correct? Yeah. So now we want to talk about what happens to the left and to the right of this. So what is the limit of f of x as x approaches negative 2 from the minus side? And what is the limit of f of x as x approaches negative 2 from the plus side? Okay? All right. So if this is approaching negative 2, right, from the negative side, so that's at like negative 2.01, let's say, right? Okay. Now, if I plug that into the first parentheses on top, I get a negative value. Right here, I also get a negative value. Is that right? So I'll get negative, negative. And if I plug in negative 2.01 to the denominator, do I get a negative or a positive value? Negative, right? So that whole thing will be negative, right? So we say the limit here will approach negative infinity. Well, there are 3 negatives now. There are 3 negatives now. Yeah. Negative, negative, negative. But as I approach negative 2 from the positive side, now it's like negative 1.99. From the positive side, if I put, let's say, negative 1.99 into the first parenthesis, I get negative, and I get negative. But on the bottom, I get positive, so now this approaches positive infinity. So do you see how that works? Basically matters in this case, not in every case. Right? Oh, right? Yeah, it depends on, right. Right, it depends on what's happening the whole time. Okay, so here we have, if we factor this, 1 minus x over 2x and x, and here we're going to get a negative 3 and a positive 1. So we have vertical asymptotes at x equals negative 1/2 and x equals 3. Okay, so what's happening? The limit of f of x as x approaches negative 1/2 from the negative side, the limit of f of x as x approaches negative 1/2 from the positive side. Okay? All right, negative 1/2 from the negative side, that's like 0.51, right? So if I put negative 0.51 up here, I'm going to get positive. Negative 0.51 here, I'm going to get what? Positive. Negative. Positive. No. I'm looking here. So it'll be negative. And then here it'll be negative. So the whole thing will be positive. Now, negative 1/2 from the positive side, that's like negative 0.499, right? Negative 0.499. Up there, it'll be positive. What about on the bottom? Well, it's negative here, and then it's positive there, so it'll be negative infinity. Okay?
Are they always like?
Are they always? Well, the sign will alternate at the asymptote if there is a multiplicity of 1, or if there is an odd multiplicity. Do you remember that? Multiplicity. So here we go. Let's do that here for the other one. The limit of f of x as x approaches 3 from the minus side, the limit of f of x as x approaches 3 from the positive side. So as x approaches 3 from the negative side, what'll it be? Let's do the positive side. It's usually easier for students. So that's like 3.1, right? If I put 3.1 on top here, we get negative. Here positive, here positive. So this is negative infinity, and I know as a result of multiplicities that this will be positive infinity. Multiplicity is basically it's the power of each of these factors, right? That's how we get like double roots. Remember? Right. So if this was like 2x plus 1 squared, then it will be positive, positive, negative, negative. Yeah. Right. Okay. So let's do these. The limit. Let's factor. So we have vertical asymptotes at x equals 0 and x equals 4. Okay. And again here, the limit of f of x, I'm just going to do it for x equals 0 for this. As x approaches 0 from the left side, from the right side, to save time, because you guys got how to do it. From the negative side, right, I get negative. So from the negative side, we're looking at, let's say, negative 0.1, all right? So here it'll be negative, 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 so that's negative infinity. And from the other side, if it was positive 0.1, then I get negative, negative here, which will be positive, and this will be positive as well, so it will be positive infinity.
So basically we require multiplicity of the vertical asymptote.
Yeah. Not necessarily always one. Like the bottom could be, let's say, x minus 4 squared. Or it could be x squared, right? Okay. So here, if I factor f of x, I get x plus 1 squared over x plus 1, which is x plus 1. So what are the vertical asymptotes? No vertical asymptotes.
There's no point. A removable distance.
Right, but we're not looking at that. Correct. Okay. Finite limits as x approaches positive or negative infinity. So we know all this by now. The symbol infinity does not represent a real number, right? Oh, one thing I forgot to mention before is when we're doing all this stuff with limits and infinities and so on and so forth, we never, ever plug in infinity into a function. Like we never say, okay, like what's infinity squared? That's never, we're never allowed. We're never allowed to say 1 over infinity. Never. Okay? We could say 1 over x as x approaches infinity, but never explicitly plug in 1 over infinity. Don't ever let anybody see you do that. Anybody who's grading any part of anything that you've written, don't let them see that. Okay? Okay. So we use infinity to describe the behavior of a function when the values in its domain or range exceed all finite values. Okay? All right. So let's talk about horizontal asymptotes. Horizontal asymptotes are defined using the infinity symbol, right? It's just a limit as x approaches infinity, okay? So the line y equals b is a horizontal asymptote if the limit as x equals infinity of a function is b, or the limit as x equals negative infinity is b. Okay? All right, so let's take a look at this function. This is x over the square root of x squared plus 1, right? And take a look at what that graph looks like. So look, the x-axis here is going from negative 1.5, I'm sorry, from negative 10 to 10, and the y-axis is going from negative 1.5 to 1.5. So as x approaches infinity, what vertical value is that graph approaching? Is it 1.5? Because 1.5 is all the way up there. So let's think about that. As x approaches infinity, if x is infinitely large, in this equation, is the 1 going to make a difference? No. So we're looking at x from the top and the square root of x squared from the bottom. Well, what's the square root of x squared? So that's just a 1, right? Now, positive or negative 1, how do we know? How do we know just by looking at the equation, not by the graph? Well, here it is.
Why is it 1?
Isn't it because the limit says approaching positive?
Okay, so take a look. This is x, right? And this is the square root of x squared, which is like x, and that would be 1. Now, how do we decide positive or negative 1? Here's how we decide. This x in the numerator can be positive or negative. But when we say the square root of x squared, it will be like x, that cannot be negative, because if it was inside a square root, it must have been defined as a positive. Does that make sense? Yes and no. Okay, because x approaches infinity, this will be 1, and as x approaches negative infinity, this will be negative 1, right? So because the limit as x approaches infinity is 1, right? Because as x approaches infinity, it is leveling off at 1. It'll never be higher than 1. It is just 1. It's leveling off at a point, at a certain value. Then we say there is a horizontal asymptote at y equals 1 and y equals negative 1, right? Or you could say y equals plus or minus 1. All right? So here, let's graph this one. So 2x minus 1 over absolute value of x and then outside minus 3. Okay. All right, so do you see how that looks? Right? Okay. So now we can do a couple of things. We can change the window here to like -1,000 to 1,000 and trace. Or I want you guys to get used to this. So take out your calculators for a minute and follow along here with me. What we're going to do is we're going to explore the table. So what I want you to do is press second window. That's the table set. That's the table setup. And here you have independent and dependent values. You can either set these to auto, which means if you go to your table, it automatically has the values in there. Or you can set it to ask, which is what I want you guys to do now. Set it to ask. And that's the independent variable, the horizontal axis, right? So set it to ask. Now, when I go to second table, right, it lets you put in values for x and it'll give you the values for y. So for example, I can put in 1,000. Okay, I can put in 10,000 or whatever, like lots of zeros, right? Oh, that's way too many zeros. I got carried away, right? So do you see how it's approaching 2, right? So the limit of f of x as x approaches infinity is 2. Well, what if I put in, let's say, -1,000? What happens then? -2.
What if my y values aren't that? Then I like -2.
We can go into the. We can go into them later. Okay, so that's how we're going to do that. Now we found the limit and identify all horizontal asymptotes. If you look at your graph, where are there horizontal asymptotes then? Right. So horizontal asymptotes are y equals -2, y equals 2. All right, moving on, we're going to talk about end behavior models. This is very, very important when we're analyzing functions when they model a specific like a concept or a quantity or whatever. So let's say you have a function that describes the behavior of, I don't know, like population growth. Let's say you have a complicated function that describes the behavior of a magnetic field or how the current runs through a circuit. You want to know what happens as t increases, what happens at an infinitely large amount of time, right? So for that, what we usually say is, okay, as x approaches infinity, this will look like a quadratic function. As x approaches infinity, this will look like a cubic function, right? So for numerically large values of x, we model the behavior of a complicated function by simpler ones that will act the same way, all right? So we say, for example, a right-end behavior model is the limit of the function as x approaches infinity. A left-hand behavior model is the limit of the function as x approaches -infinity. Okay? So what these mean is, listen, so you have f of x, okay? You have f of x. As x approaches infinity, what is a simpler function that looks like? G of x, right? And how do you say mathematically that f of x and g of x are the same? Well, when you divide them and you get 1. So that's what that's talking about here. Okay? All right. So here it says match the function with the graph of its end behavior. Please don't graph. and try to match it, because none of them will match the function as they are. Okay? Look at number 1. That is a complicated function. If I was walking down the street and I saw that number 1 on a billboard, right off the bat, I don't know what that would look like. And maybe, you know what, I don't really need to know what that would look like. Maybe that is the function of like an electric field. Okay? And I want to know what happens at t equals infinity. Is this circuit gonna blow up? Okay? Well, let's see. What I do is, just like we did before, I take the first term, or the highest degree and the highest degree. So this will be y equals 3x cubed over x, 3x squared. That's like a parabola that's facing up, isn't it? Which one of those does that match? B. You see? Here, y equals negative x to the 5 and 2x squared. So that's negative 1/2 x cubed. Right? Which one is that? A. And let's see if 3 is C. Well, y equals negative x cubed over x, negative x squared. Yup, it is. Okay? So I know everybody, like, you know, tries to graph those 3 and they're like, oh my God, none of these are the same. Well, because they're not supposed to be. So this is the end model behavior, right? End behavior model. This is the end behavior model. Because a lot of times, okay, so for example, there's a gas leak. Okay? There's a gas leak and it behaves and it spreads according to a model, let's say, right? You want to know, 50 years down the line, how is this going to affect us? So we say, okay, as t approaches infinity, this is going to have a 1 over x model. That means as t increases, the value of the, you know, how much is spreading is also going to decrease to 0, right? Whereas if at t equals infinity, it was a y equals x model, then it's just going to keep increasing. Another way this could be useful. Yeah, the end behavior of this will be the same as the end behavior of this. The end behavior of 1 will be infinity, and its end behavior model will be infinity. But now I have a simpler function that I can carry around with me. Okay, here, find a power function. So here we go. So here, the power function will be, let's write g of x, will be negative 2x squared. And then what are the horizontal asymptotes? None. Right? Because 2x squared does not have horizontal asymptotes. Here, g of x will be 3, because we take this and this. So the horizontal asymptotes will be y equals what? The end behavior is 3. So when x equals 5,000, what's y? When x equals negative 5,000, what's y? 3. So it's 3. All right. Let's do continuity. I know we've touched on this before as well, but now we're going to do it more formally, calculus style. Any function whose graph can be sketched in one continuous motion is said to be continuous. Okay, it's an example of a continuous function. Now, continuous functions are used to describe a whole bunch of things in the universe. This function here is a continuous function. I like to, you know, one way is to, okay, like you can trace it without taking your finger off of the page. Think of it as a roller coaster. It's a nice, like there are no bumps on the way, right? Just some elevation increases and decreases. That's all. Okay. Sometimes we don't care if the function is continuous throughout its lifetime. Sometimes all we care about is the function continuous at a certain point? Okay? And how do we tell if a function is continuous at a certain point? Well, it's a very, very simple test. In order Okay, so we can look at it at an interior point and at an end point. So interior point, like some random point in the life of the function, all right? A function is continuous at an interior point if the limit is equal to f of c, right? So here, for example, take a look here. Whoa. Take a look here. What is the limit as x approaches 4? As x approaches 4? Infinity? As x approaches 4, it's a 1. As x approaches 4 from the right side and the left side, that's approaching 1, right? Okay. What is f of 4? It's also 1. So since the limit and the value have the same are the same value, then it's continuous at that point. Or you can just look, right? So basically the limit has to be the same as the value there. Now, what if we are talking about an end point? Okay? What if we're talking about an end point? So suppose you have your function like this. Okay? But I'm only looking at this from A to B. Okay? That's it. The rest I throw away. So now I want to know, is it continuous at A? Is it continuous at B? Well, if I'm bound by this and by this, at A, I can't do a two-sided limit. Can I? No, because it doesn't exist from one side. So for A, what side limit can I do? From the positive side. And at B, what side limit can I do? From the negative side. So in those cases, all I need to do is see if the limit from the one side is the same as the value, and then it's enough to say it's continuous. Does that make sense? Cool. That's what all this says. Okay? Now, if a function is not continuous, it's discontinuous at C, and C is a point of discontinuity. Okay? All right. There are 4 types of discontinuities. Removable, jump, infinite. We've done all those. Yes? New is oscillating discontinuity because the limit doesn't exist. So how could it be the same as the point? Right? Yeah. Correct. It is. And a removable discontinuity is just a hole, and a jump discontinuity is a jump. Piecewise, and oscillating is just a fantastic sinusoidal function. Yeah. I'm trying to rush a little bit. Okay, so find the intervals of continuity and the points of discontinuity and identify each type. So here's how we do this. This one, when we factor, will be x minus 2, x minus 1 on the bottom. So I have vertical asymptotes at 2 and 1, correct? At x equals 1 and x equals 2. So if I look at a number line, this is 1 and this is 2. This function is not defined at 1 or 2. It's discontinuous there, but it's continuous everywhere else, right? So I say this is continuous from negative infinity to 1, 1 to 2, oh, 2 to infinity. Yeah, the parentheses, correct, the parentheses. Now, then we're going to say there is not a removable. There are infinite discontinuities at x equals 1 and x equals 2. That's how we write it. The most you could change here is maybe put a comma instead of the end if you want less writing. But this is the way I want it written. Here, where is there a discontinuity for absolute value x minus 1? There's no discontinuity. It's continuous everywhere. There's just no holes, no jumps, no gaps, nothing. Never. ln of x minus 1. Okay, so ln, remember what ln looks like. Okay, so it's continuous from 1 to infinity. Right. Otherwise, it would have been 0 to infinity. Okay, can it hit 1? Can it hit 1? No. Right. Because x minus 1 moves it to the right one. Okay, so this one here, it's 2 over x. Not 1 over 2x. 2 over x, zoom 6. Okay, do you see that? Where is there a discontinuity? At x equals 0. So there is an infinite discontinuity at x equals 0, and it's continuous, negative infinity to 0, whoops, 0 to infinity. Yes, a vertical one. No. I'm going to graph this and answer the questions that follow. So the first one is defined from negative 1 to 0. I plug in negative 1 and I get 0, and that's a closed circle. At 0, this is 1, it's an open circle, and it's a parabola on inside. From 0 to 2, it's x plus 1. So at x equals 0, it's 1, and it's closed, so we just go ahead and close that, fill in that open circle. And then at 2, it's 3. That's open. At x equals 2, it's 4. You see that? It's just a point at x equals 2. And then at x greater than 2, it's negative x. So here it's negative, and it goes down like that. Okay. This was Algebra 2/Semester 1. So if you have any questions, come to bonus, not during class. Okay? Now, does f of negative 1 exist? Yes. Does the limit as x approaches 1 of f of x from the negative side exist? X approaches 1 from the negative side? It exists. 1, not negative 1, 1. Does the limit as x approaches 2 from the positive side equal f of 2? Well, what's the limit as x approaches 2 from the positive side? It's negative 2. And what's f of 2? 4. So it's a no. Is f continuous at x equals 0? Yes. Because it's going this way. So it's here. Okay. You only go from the one side. All right. Here we go. One more. Let's graph this one. So as x is less than 2, this is a 3. 3 minus x. So at 2, this is going to be 1, and it's an open circle. At x equals 2, it's a 2. And then greater than 2, it's 1 half x, right? When x is 0, it's 3. Okay. And then it's at x equals 2, this is a 1. And it's open. All right, so point of discontinuity. Where is there a point of discontinuity? At x equals 2, and that's a removable discontinuity at x equals 2. Okay? Now, okay, here, I need to finish this one. Okay. This next one we're going to do without graphing because you need to be able to do it without graphing. Okay? All right. We have one partition at x equals 0. So plug x equals 0 into the first function and you get 0, right? Into the second function, you get 6. Is that a discontinuity? No. That's a jump discontinuity at x equals 0. Now, when x equals 3, the top is 6, the bottom is 6. Are we good? Okay, hang on. You have the same value. Fine. But now you have to make sure that it's a closed circle, which it is a closed circle, so there is no discontinuity there. Okay? No discontinuity. It's continuous. No. Now, hang on. There's nothing to say here. A continuous function is continuous. If a function is continuous on an interval, it's continuous at every single point. Now, take a look here. A continuous function is continuous at every point of its domain. Take a look here. What's the domain of this function? Okay. On its domain, from negative infinity to 0, is this continuous? Yeah. From 0 to infinity, is that continuous? Yeah. So that's a continuous function. Yep. Because a continuous function is defined as being continuous at every point of its domain. Okay?